So today we will start another part of design, but let me get the story from the beginning. We started so far in this course that you have area of land and we would like to build a warehouse. So first step, we will start to draw the layout. So I selected, for example, this truss as my main system. And keep in your mind, as I told you last meeting, that the width or the span of this truss should matching with the width of this area. So this span equal the width. I decided to put this main system or this truss to be spaced by equal spacing. Your spacing can be 20 feet, 25, 30, but keep in your mind, we need to maintain equal spacing, which is S. Also, from this truss that you created, that you suggested, the horizontal distance is called A, the inclined distance is called A prime. This is the first step. Second step, I will start to make loading. I need to figure out how much did load, how much live load, how much wind load, how much snow load. Keep in your mind that your truss, which looks like this, all loads are vertically downward, except that one for wind load. The direction of these wind loads will be perpendicular to the roof or the surface of the truss, like this. Suction. That makes sense? Anyway, I will define this truss and these loads on RISA 2D to figure out the structure analysis of this truss. Structure analysis of the truss means you are going to find the internal force in each member. So the final conclusion, you will have this truss with diagram or with diagrams. For example, you will have this diagram on this member, another diagram on this member, another diagram on this member, and each diagram will give you a value. This value represents P ultimate on each member. What is the P ultimate on each member? What is the P ultimate on each member? What is the P ultimate on each member? That makes sense? Some of these values are tension. At the top, at the bottom will be tension. This is the bottom or the lower chord. At the top, it will be compression. The web, the vertical or inclined member, I don't know exactly, but some of them will be tension, the other will be compression. So the final conclusion right now, we have tension member and we have compression members. So we will start to third step, design. If you would like to design your tension member, if your member is tension and you would like to design it, okay, your P ultimate from RISA equal 0.9 if yield area gross. Then go ahead and define area gross. How much? Because everything in this equation is known. The P ultimate from Riza, if yield based on the type of steel, 0.9 is constant, so you can figure out the value of area gross. Open your table to select angle, one angle or double angle if you want. One angle or double angle if you want. And I give you guide last meeting that the top chords and the bottom chords will be double angle, and any inclined member or vertical member, which is called the web of the truss, will be single angle. This is just a recommendation. If you decide something else, it's up to you. Just to give you this hint one more time, these are called lower chord. These lower chord, we recommend to use double angle. These members are called upper chord. I'm gonna use double angle also. These members are called web of the truss. I'm gonna use single angle. If you decide something else, I cannot say it's wrong, but it's not economic. That makes sense? Anyway, once you get your area gross and you open your table and find a reasonable or suitable angle, I need to make a check, another check, that your P ultimate is smaller than or equal 0.75 if ultimate area effective. And keep in your mind, the area effective can be assumed 0.75 area net, and your area net equal area gross minus summation, if you remember, d whole plus 1/16 time thickness. We covered all of this stuff when we design tension member. Last meeting, we started to design a compression member. The first step, I'm gonna assume member. I'm gonna open my table and select a cross section. Unfortunately, we don't have guide for compression member. I'm gonna assume from the beginning a member. I'm gonna assume a cross section. So this cross section has area gross. This cross section has section properties IX, IY, RX, and RY. I will say or make sure your P ultimate is smaller than or equal 0.9. I think area gross time FCR. Is it FCR? Cannot remember. Yes, it's FCR. FCR is the critical stress. And we have two values for FCR, I think. I cannot remember. Is it FCR or something else? Anybody can help me? Do you remember? Is it FCR? Any help? I think it was FCR, and we have two values based on the relationship between KL divide R and 4.71 square root E divide F yield, I think, is greater than or equal or smaller than or whatever. So we need to make sure this equation is satisfied. If it is, that means what you selected will be safe. If it's not, unfortunately, you have to select a bigger cross-section to make sure it will be safe. Any question so far? This process to design your tension member and the compression member must be done for each member in your truss. If you have 100 member, you need to design the 100 members. If you have 50, you need to design all of them. I highly recommend, if you are aware of Excel, you can use Excel. So you can put the value of P ultimate in Excel. Excel can help you to figure out the design. Today, we will do another design of connection. We will start to design of connection. I'm gonna start with the bolted connection. Keep in your mind that we have 3 different types of connection. You can connect these members together by welding or by bolts or by rivets. I think using rivets is no longer available. You can find this type of connection in very old building or bridges. Old building or bridges is built in 1950s or 1960s. You will find all the connections are rivet connections. But so right now or nowadays, we are using bolts or welding. I will cover today the bolted connection. Probably next week, we will do the welding connection. Connections of structure steel member are of critical importance. Failure of structure members is rare. This point is very important. This one is very important. To have a failure in the member itself, it's very rare. But most of structure failure are the results of poorly designed or detailed connections. If you expect, or if this happen in the future, that you have failure in this member, we can say 90 or 95% of this failure will be due to this connection, not in the member itself. I can say the connection will be fail before any failure in the member. So keep this in your mind. You have to make sure your connection is designed correctly. Modern steel structures are connected by welding, bolting, either high strength or common bolts, which is called ordinary, or by a combination of both. We have welding and we have bolted. Sometimes we have both of them at the same connection. But rivet is a very old fashion. We no longer using rivets in our connections. Do you have any questions so far? Guys, do you have any questions so far? I have question. And I need one of you to answer this question. What is the expectation of the design? Okay, I would like to design my connection. What is the final product? If you decide to design your tension member, the final product that you selected a member. If you would like to design compression member, the final product you selected a member or cross section. Anybody can tell me what will be the final product if you design bolted connection? What is the final answer? Anybody can tell me? What will be the final answer? Guys, do you hear me? Thank you. Yes, Mitchell. Yes. I will say number of bolts. Diameter is, we don't have choice for diameter, because diameter, if you go to Lowe's or Home Depot, you will find already ready bolts. So the diameter of these bolts will be ready. We don't have a choice. You will see here a table. This table, this one. These are the available diameter. These are the available diameter: half inch, 5/8 inch, 3/4, 7/8, 1. You can select one of them. Once you select one of them, okay, go ahead and tell me how many. Number of bolts. Yes, sir. So if you look to this photo or this picture, you will see here how many bolts? 1, 2, 3, 4, 5. We have 5 bolts. So what is the diameter of each bolt? Then you are designed your connection. So the final product, we need to figure out how many bolts needed to connect your member to this connection. Okay? So it's a very, very, very simple design and a very simple step. But before this, I would like to share few concepts about the failure modes. If you have failure in the connection, your failure can be something like this, or like this, or like this, or like this. We have bearing failure because they hold this hole and you have bolt inside this hole. So we have bearing of the member on this bolt. As you see here, this part of the member trying to move this way and the other part trying to move on the other way. So we should expect shearing on this member, on this bolt, shearing. And the material of the member is already bearing on the bolt. So we can expect a failure in the member, fracture like this one, or this part, or we have bearing failure. So we have 3 different types of failure. The whole member will be broken like this one, which is called net tension, or part only of the member, this part will be sheared off. Or bearing, we don't have complete failure, but the hole became bigger, or it was circle became ellipsoid, ellipse, like this one, ellipse. Okay, so failure of the connected part because of the bearing exerted by the fasteners or the bolts. Failure resulting from excessive tension, shear, or bending in the parts being connected. We have different types of failure. So we need to avoid all of these types of failure. We don't like any of them. One more thing. Sometimes your connection is called the single shear connection or single shear bolt or double shear connection. What you mean by single and double? Let me explain it here. So if you have this part or this member and this member, the 2 members are connected together by this bolt. So keep in your mind that this part is moving this way and this part is moving this way. So anybody can tell me how many shearing plane? I think you should expect a failure at this one, because this part of the bolt would like to move to left following this part of the member, and the lower part of the bolt would like to move to right following this part of the member. So we should expect shearing at this location. How many plane of shearing? We have only one plane, so it's called single shear. This is the meaning of single shear. However, sometimes we have this member and this member connected to this member with a bolt, and your bolt looks like this. Keep in your mind, this part of the members, this part of the member will be moved to left. We have a force here. And this part of the member or the connection will move in this way. So looks like this part of the bolt and this part of the bolt would like to be moved following this force in this member and this member. However, we have this part of the bolt, I'm talking about at the moment of failure, would like to move to right following this force. So how many shearing plane do you have in this one? We will have shearing here and we will have shearing here. So your bolt will be broken or will be sheared off at two locations. This is called double shear. Keep in your mind, we have single shear and we have double shear. This is the meaning of this slide. The bolt loading in the connection in the figure with only one shear plane. But in this case, it's a double shear plane. So the fastener shank shows that each cross section is subjected to half of the total load. So we have double shear and we have single shear. Keep this in your mind. Keep this in your mind. The second thing, this part of the bolt is subjected to this force, and this part of the bolt is subjected to this force. However, if you have a force here in this member, we will have F divided 2, and this member will have F divided 2. That means this part of the bolt will be under the effect of F divided 2, and this part of the bolt will be under the effect of F divided 2. So the applied force on the bolt will be half. However, in this case, the same bolt, but the applied force on the bolt will be the same force F. So if you can make your connection double shear, that will be good or better. Single shear, that means you have a lot of force that must be transferred by the bolt. Okay, where is the answer of my question? How many bolts I need? Here is the answer. The required number of bolts at each end of the member equal P ultimate from Reese analysis. Oh my goodness. Do you remember the P ultimate, which is coming from structure analysis, which is the diagram on each member? We have P ultimate. This P ultimate will be divided by phi Rn. Phi Rn is called the design shear strength of one bolt. The design shear strength of only one bolt. How can I figure out this value? Yes, I can figure out P ultimate from Reese analysis. That's fine. Or 1.2 dead load plus 1.6 live load. Or what about phi Rn, which is a design shear strength? We have expression here. Phi Rn equal 0.75 N FNV area bolt. So we have three terms. Let me talk a little bit about each. The first term, N, is the number of shearing plane. We have two cases most of the time. We have single shear. If you have single shear, your N value will be 1. If you have double shear, your N value will be 2. That makes sense? So N is the number of shear planes, N equal 1 for single shear, N equal 2 for double shear. Area bolt is the cross-section area of the bolt. Since your bolt has a diameter, I can figure out the area bolt equal by divide for this diameter, the bolt diameter of the bolt. I can label it the bolt. That makes sense? So keep in your mind, your bolt has a diameter. This diameter can be used to figure out the cross-section area of your bolt. So far, looks good. 0.75 looks like 0.75 is the value of phi. N is the number of shearing planes. We have N equal 1 for single shear, N equal 2 for double shear. Area bolt is the cross-section area of your bolt. What about FNV? FNV is the nominal shear strength. This is based on the type of your bolt. We have a table here. I'm gonna use this column of your table, this one. Based on the type of your bolts, we have different types. We have ordinary bolts. It's called A307 bolts. This is a kind. We have the second type is called the high strength bolt. We have two grades, grade A and grade B. So these are the different types of bolts. So before you design your connection, you have to select what type of bolts you are going to use. For example, if you decided that your bolt is ordinary bolts, that means the value of FNV, which is this one, it will be for A307 bolts, this type of bolts, this one, your value will be 27 KSI. Your value will be 27 KSI. So if you decided that your type of bolts, ordinary bolt A307 bolts, your value of FNV will be 27. I will put here 27 and then N, how many shear plane, 1 or 2, area bolt, what is the cross section of area bolt, multiply them together by 0.75. That means I can figure out the value of Rn, put your value in as the denominator, divide P ultimate by this denominator, you can figure out how many bolts you need. Any question so far? Any question so far? If you have any question, just let me know. Okay. If your bolt is the second type, which is high strength bolt. In high strength bolt, we have two options. The first one is grade A. The second one is grade B. Assume we have grade A or group A. If you have group A, we have two options. Hey guys, I'm not sure if you are familiar with this or not, but sometimes your bolt is fully threaded. Can you see the thread? So the whole shank of the bolt is threaded. However, sometimes we have a different type of bolts, half or part of the bolt is threaded and the other part is flat. So if your type of bolts is high strength group A, you have to tell me, are you in this case or in this case? your bolt is fully threaded or partially threaded, only part. So for group A, bolts when 3 threads are not excluded from the shear plane, which case? The second one, bolts when threads are excluded. So this one is this case. In this one are not excluded, that means you have threaded part at the location of your shear plane. Whatever the case, you decided, for example, we are in this case. So the value of F in V will be 54. If you are in this case, the value will be 68. If your bolt is group B, it's a high strength, but group B, that means we have two values, 68 and 84. Keep in your mind, these two cases are explained here. In this case, your threaded part is only at this part. That means the shearing plane is away or threads not in the shear plane. In this case, the threaded part is fully for the whole shank of the bolt. That means your shear plane going through the threaded part. That makes sense? This is the difference between this one and this one. I can explain it in more details. So the first case, that threads are not excluded, that means you are in this case. If the threads are excluded from the shear plane, you are in this case. That makes sense? As I told you, once you decided what is the value of F in V, go back here and put F in V and the area bolt and the number of shearing plane time 0.75. You can find the shear strength, the design shear strength. Go ahead and put it as a denominator. P ultimate divide this denominator. You can find the number of bolts. I have question. If this number equal 4.1 or equal 4.9, do you think we can have a number of bolts as a decimal? So 4.1 will be how much? And the 4.9 will be how much? Any help? Thank you. 5. Whatever your decimal, I have to round up to the next number. Odd or even number, I don't care. Odd or even number, probably it's not a big deal, but your number must be integer and be rounded up to the next number. Does that make sense? Let's do an example here. I will talk about this one next meeting, but yes, let's do this one. I will solve only one example today, and we will continue on Monday. So we have a plate, 3/8 times 6 is used as a tension member to resist a surface dead load. So your dead load equal 12 kb. Your live load equal 33 kb. Because we don't have RISA, we don't have a real problem, so we are given some information. This information will help us to figure out the P ultimate according to ASCE equal 1.2 dead load plus 1.6 live load. But in the real life problem, we should have structure analysis for your truss, so you can figure out the value of P ultimate from RISA. 1.2 times 12 plus 1.6 times 33. Your value will be 67.2 kb. This is the first step. Second step. This member will be connected to 3/8 inch gusset plate. with 3/4 inch diameter group A bolts. Here you go. So the D bolt equal 3/4 inch. And this bolt is group A. Determine the number of bolts required for this connection. Okay, I need first to figure out what is the design shear strength of your bolt. So I need to figure out this expression. Phi Rn equal 0.75 NF NV area bolt. Phi Rn equal 0.75 N area, I'm sorry, F NV area bolt. Since the problem did not say anything about that you have double shear or anything, just we have this plate connected to another plate with bolt. So looks like we have single shear. It's a single shear. So your value of N equal 1. Since you have group A, so I can figure out the value of F and V. For group A, looks like we have two values, 54 or 68. If you read your problem carefully, we are not given enough information about this case or this case, so you can assume one of them. So if you used 54, I'm gonna assume that the threads are not excluded from the shear plane. If you use the 68, you need to say, I assume the threads are excluded. That makes sense? It's up to you because we don't have enough information in the problem. So are you going to use this type of connection? The shear plane is away from the threaded part, or you will have threaded part going through the shearing plane. It's up to you. Are you going to use this type of bolts or this type? Fully threaded or partially threaded? It's up to you. I'm going to use the first one, 54. So you will assume it 54. The area bolt, since you have the diameter of your bolt, I can say the area bolt will be pi divided 4 times 3/4 square. So I can figure out the design strength, the design shear strength of your bolt, 0.75 times 1 times 54 times pi divided 4 times 3/4 square. Your value equals 17.8 kip. This is the design strength for only one bolt. So the required number of bolts will be P ultimate divided by phi Rn. P ultimate from structural analysis 67.2. The design strength right now is 17.8. So the required number of bolts will be 3.75. I'm gonna use 4 bolts. That makes sense? We will use 4 bolts to connect the two members.